Okay, so this is the continuation of our lecture from last time. This is actually a few slides, or one slide sort of back, just to remind ourselves, what did we do and where are we going? So what we're establishing is a procedure for calculating the amount of material, the amount of product, when we have limited amounts of all of our reactants. So reactants being like the ingredients in our recipe. And so we call this a limiting reactant question. And there's basically sort of a strategy rather than like a set of rules we should just memorize. It's more of a, you sort of get the strategy down and sort of the idea behind what to do down, rather than strict sort of memorization. So the idea is that we do what I like to think of, you just do the same calculation twice. If you're given quantities of both reactants, or maybe 3 or 4, who knows? But when you have quantities of multiple reactants, you're going to do the calculation of how much product do I make, starting with each of them. And so in that regard, there's sort of this strategy. You get the givens for reactant number 1, you turn them into amount of product. Givens from reactant number 2, turn it into an amount of product, and that's using the recipe, right? And the idea is this is a mole recipe, so that's why we say make sure that our conversions allow us to get to moles, because that's how we use this recipe. And then we say, once I get the amount of product, right, I have to compare the same product. So this is why they're both 1 and 1. Product number 1, product number 1. Then by calculating for the same product, I can just go by what size is bigger versus what size is smaller. Our smaller answer is the actual amount we expect to make, also known as our theoretical yield, because it means that we'll make a small amount and then run out of that reactant. So that indicates that the reactant that was used to generate the correct answer is called the limiting reactant, because it limited us to a small amount. And by, and then terminology, the other reactant or reactants, if there are more, are called the excess reactant because they did not get used up completely. And so we practiced with this question. This was, we were asking how much product, in this case, lithium fluoride, a compound, a crystalline solid compound, how much can we produce from 10 grams of lithium combined with 10 grams of fluorine? So now we need to assess, well, which one will get used up first? And so we did the calculation for lithium as our warm-up, and we got an answer. If I use up 10 grams of lithium, I will make 37 and some change grams of product. And then we said, let's do the same calculation again, but starting with the other reactant. So that's for 10 grams of fluorine, and then doing the same calculation that we've been practicing for 1.5 lectures, this mole recipe conversion, stoichiometry, we get another answer, 13.7 grams of product. What we say is that the two, of the two, the indication is that we will use up the fluorine because it will produce the smaller amount of product. And I think I have a visual here where if we sort of look at it like a number line where the amount of lithium, the amount of product lithium fluoride is being produced by each, we see it as, well, there's a cutoff here on the number line. Once I reach this point, my bar for one of my reactants has disappeared. In order to make product, I need to have both of my reactants contributing to making the product because the recipe has 2 ingredients. So once my 1 ingredient gets used up, now even though I have excess of the other, I can't do anything with it without the 2nd ingredient. And so this is why we say the limiting reactant stops the reaction from continuing, and it indicates which one we should pick for our answer. The answer is the one that gives us the smaller value. And then I mentioned briefly before, what do we do with the other number? Because we made two calculations, right? So this is what I mentioned last time. What do we do with this other number? We ignore it. It has no physical meaning. Its only purpose was to make the comparison. Now we can ignore it. This is going to be our answer. So to sort of summarize,
Professor?
Yeah, question.
I was just wondering from the previous problem, because I forgot from yesterday. Generally, when we're looking at the word problem, how can we tell which one is our limited reactant?
You have to do the calculation. There's no way to safely guess every time without doing these two calculations and picking the smaller of the two. Or if you're really good, you could do it as mental math, but that's really hard. I mean, there are ways to do it mental math. It would basically be doing all of this in your head, essentially. But the safest way, and in my opinion, the best way, is to actually do the calculations starting with Givens number 1 and then Givens number 2 and picking the smaller of the two.
Got it. Okay.
Yeah. Okay. So the reactant that produces the least product is our limiting reactant and is completely consumed or completely used. Now the other one is called the excess reactant, and it's because there's going to be leftover. So we can actually continue the calculation and ask, well, how much of the excess reactant is left over? So that's going to be sort of the cherry on top of this. Not only can we calculate how much product we make, but we can calculate the remaining amount of our reactant or reactants, if there's many. So this is just continuing, adding on to get the full what you could expect with problems. So not only are we sort of adding the first part of our question from the warm-up, we added the second part that we just finished, and now we're adding a third part, which is sort of the full, this could be the question. What is the maximum amount of lithium fluoride in grams that can be produced from 10 grams of lithium and 10 grams of fluorine? How much of the excess reactant remains after the reaction? So because this is a continuation, we can start by, well, we did most of the calculation already. We figured out how much product was made, and we figured out which was our limiting reactant. So just to remind ourselves, we found out that the smaller number we get from the fluorine. So that's going to be our limiting reactant. And by, process of elimination, the other reactant or reactants are going to be considered the excess reactant. So that means the lithium is the excess reactant. So how do we figure out what's left over? The strategy is find out how much of the excess reactant is used up by the limiting reactant. And the leftover is the distance between the initial amount and the amount that was used. So this is our basic strategy. We're going to say Givens and desired again. And this time we're going to take the Givens for the limiting reactant, and we're going to take it to the excess reactant. So in our case, we're going to take the Givens for our fluorine, and we're going to try to calculate how much lithium, since that was the excess. So it's going to be another sort of stoichiometry, because stoichiometry is always the how much questions that are involved with chemistry. How much am I going to make, or how much, in this case, how much is used? So that's the key difference. When it comes to how much is left over, we're going to use the limiting reactant one more time, starting our calculation, only this time we're going to use it to calculate how much excess reactant is going to be used. So here are the Givens one more time. 10 grams of fluorine is my limiting reactant given, right? And it gets completely used up. That's what limiting reactant means. It means that it stopped the reaction because it got consumed. So now our desired, instead of being the product, is how much of the other guy is going to be used when combined with this much. So that's basically the rationale for what we're doing. We're going to take the amount of limiting that we have, and we're going to see, well, how much of the excess of the ER do I need to combine with it? So from our previous calculation, we've identified the amount of product, and we've identified the limiting reactant. Now, once we've identified the LR, we're going to use the LR one more time to calculate how much ER is used. So to use the abbreviations because it's kind of simpler. So again, it's going from a quantity of one thing in the recipe to a quantity of the other. So what kind of question is this? It's stoichiometry. And so I mentioned that there's a strategy that I think is really helpful to write every single time. The strategy that glues the entire problem together is we're going to take moles of given and turn it into moles desired using the chemical equation. That's going to be the glue that holds every single stoichiometry problem together. And then I mentioned that once we've identified the given and the desired, we go ahead and replace it with the words. So the given in this case is my F2, because that's what I'm starting my calculation with. So that means my strategy is going from moles of F2 to moles of Li. Now I just connect my flow chart of steps to sort of see what the whole picture is. I'm going to take grams of fluorine and turn it into moles of fluorine. Then I'm going to use the balanced chemical equation to turn it into moles of lithium. And then I'm going to get grams of lithium. I don't know about you, but I think we can do this. So we're going to rewrite the given. 10.0 grams of F2. And my first hurdle to jump across is to go from grams to moles of fluorine. What am I going to do for that? It's like, oh, we've done that a bunch of times. Molar mass, right? We have to be careful because it's F2. So we have to add up 2 fluorines. And then we just need to make sure the units are put in the right place on the fraction. So if we look at our periodic table to find fluorine, by now you should be getting good at finding these elements on the periodic table. So fluorine has a molar mass of 19. So F2 is going to be 38.00 grams per mole of F2. So grams of F2 per mole of F2. And I'll go ahead and put it like that. Molar masses do have sig figs, and remember, it was 2 decimal places in the digits. So this means this is a 4 significant figure number. And so our grams cancel, and we've made it to the first, over the first jump in our strategy. We've made it to moles. Now our next strategy, the central theme of all stoichiometry problems, is to take your moles of your given to desired, moles of desired, using the chemical equation. So what am I going to do that? Well, it's going to involve a fraction. All right, here's a fraction. We're going to locate the given and the desired. 1 fluorine, again, looking for the coefficient, 1 fluorine needs 2 lithium. Just a side note, notice my wording for a second. Because fluorine and lithium are reactants, I don't say that fluorine makes lithium because they're actually both ingredients. So the correct interpretation isn't that the 1 fluorine makes 2 lithium. It's that one fluorine must be combined with 2 lithium to make product. So just FYI on interpretation of that. So we just want to be sure we understand what all of these pieces mean. But that's going to make our fraction. 1 mole of F2 is going to be 2 moles of Li. And that's going to allow us to cancel the unit. Now we get past the second hurdle. Our last is to go from moles lithium to grams lithium. That's going to be a final molar mass conversion, moles to grams. It's the opposite kind of conversion because it's going the other way. But we do it the same way. We look up lithium and we're going to make sure we put it in the fraction correctly. It's 1 mole of lithium is 6.94 grams. So I'm going to put 1 mole on the bottom. Mole of lithium is 6.94 grams of lithium. And we just double check we have it right. There we go.
So, Professor, the middle conversion factor, 1 mole of F2, right, or 2 moles of lithium per 1 mole of F2, is that based on the left side of the balance equation?
Exactly. So since I want fluorine, F2, and lithium, I'm looking for just those coefficients. And so that means I'm only focused over here. And that's basically how it works for all problems. You're just going to look for where they come up in the equation and take their coefficients to be the parts of the fraction. So that's exactly right. 1 mole of fluorine, 2 moles of lithium. And then we plug it in. This unrounded or not rounded correctly answer is 3.652 with the significant figures. There's 3 of them, so they end there. So this is my last sig fig. But we have to be careful because what this calculation is doing for us, it is telling us how much ER combines with the LR. So this is not actually the desired answer. This is how much ER is used. So then that means, what do we do to find out how much is left over? It's going to be the difference between the initial and how much was used up. And so there it is. And so because the last step is subtraction, I'm going to go with 1 decimal place versus 2 decimal place. And this is why my leftover is 6.3. And so this is how much lithium is left over by the reaction. Okay. So putting it all together, we can kind of create a table to organize and kind of see what we made or how we did, what our answers all together are. So the original question, or I guess the full question, is what is the maximum amount of lithium fluoride in grams that we can produce from 10 grams of lithium and 10 grams of fluorine? How much of the excess reactant remains after the reaction? So let's remind ourselves what we did and how we got our answers, and then put them into this table. So what was our first step? Our first step was to consider both calculations. So starting with 10 grams of lithium and 10 grams of fluorine. Oh, I forgot to mention, notice that at the beginning of a reaction, we don't have any product. So that's why this is 0. I did both calculations and I got 2 numbers for the possible amount of product we made. What we ended up doing was we picked the smaller of the numbers. So that's where we got this number as our final answer. And to remind ourselves, that final number was we were going to make 13.7 grams of LiF. And that was choose the limiting reactant. From that point, we were able to do a very important task. We were able to label the reactants as either being the LR or the ER. And what we found is that because fluorine was the smaller answer, this is the limiting reactant. And then by association, that means lithium is the ER, the excess reactant. So that's 2 important things that we get from doing this. By doing the calculation twice, we can pick the correct amount of product we're going to make. And then we can assign, that means the one that I chose was the LR. And the one that is in excess is the ER is the remaining one, or ones, if there's more. Then what did we do? We use the LR in all subsequent calculation. The LR was what we used to figure out that there was 3.652 grams of Li used. And from subtraction, we determined that that meant that 6.3 grams of Li left over. Now, there's a final box here that we didn't talk about yet. It's how much mass of F2 is left after the reaction. And, oh no, we didn't do a calculation. Uh-oh. Do we have to go back and do one? Maybe we should bust out our calculator one more time. No, this is something that trips up students all the time. The definition of a limiting reactant is that it limits how much we make because it gets completely used up. So how much limiting reactant is left at the end? It's going to be 0 grams of F2. So one thing to note is that while the calculations can be tedious, by knowing the definitions of things, knowing what they mean, it can help save you time. Because if you tried calculating, you could do a calculation, but it's kind of trivial. It's kind of like not necessary. You'd be calculating how much fluorine do I use with 10 grams of fluorine, and you'll find out that it's 10. And so if I have 10 grams and I use up 10, I have 0 left. So we have to be careful. But one thing that I want to emphasize just by what I'm showing in this sort of full table is notice the arrows of how the information goes from given to desired. What I'd like to emphasize is that the limiting reactant actually becomes the thing that dominates all of your calculations. And that's the critical part about labeling the limiting reactant correctly, because the limiting reactant is what you use to calculate products. Then you go back and use the limiting reactant to calculate the remaining, because it required us to figure out how much of the ER gets used up. So we go from limiting to excess, and we get the remaining. And by subtraction, we get the leftover. And then from the limiting reactant, we can automatically get how much of it is left over. If this is truly the limiting reactant, it should, by definition, be completely used up. And so it's 0. So even though a limiting reactant question is more complex in that there are more steps, what I hope to sort of clarify and emphasize is that really it's one strategy, and almost in some sense it's copy pasted a lot, because you're going to start from the same number each time. So a lot of the work that you did can be copy pasted essentially. And then you just change a little bit, in the middle and the end. But it really, to understand what to do, the actual math, is really a conversion. We've been doing a lot of conversions. Really, the challenge of this kind of problem is understanding the definitions, vocab. What does it mean to be the limiting reactant? What does it mean to be the excess reactant? And how do they connect to each other? So that's the thing that we have to emphasize with these.
Professor?
Uh-huh.
Do you have any, have you posted any sample problems for questions like these?
Uh-huh. I even have a video tutorial where I give you the question, and then if you'd like, you can just find, the answer is already given in the text, but if you'd like to go through it, you watch the video and I do it for you.
Okay.
So yeah, there are, I believe, at least two videos of that. And then I have the PDF. Again, this is module 9. So that would be CP 9.2 probably, but I'd have to verify that. But there are problems, definitely, both in video form and just text written with the answer. So the basic idea for this kind of problem, you have maybe 2 reactants going to 2 products. You're going to determine the limiting reactant, the excess reactant, and product number 1. So you're going to take the givens, you're going to do the calculation, you're going to take the other givens, do the calculation, and then what do? We pick smaller, ignore bigger. Again, the bigger answer doesn't have a physical meaning in the context of the question. It's just there to decide which one came out bigger. How do we go from there? The arrows from given to product, that's the goal is the mole. Remember, the central theme of stoichiometry is moles of the given to moles of the desired, and you make a little flow chart to remind you, how do I connect the pieces? And the rest just becomes a conversion problem where we use the chemical equation itself sometimes or all the time for the conversion as well. So that's the sort of new piece to this. But once we do that, we can use the limiting reactant in all of our subsequent calculations. Remember, the limiting reactant controls when the reaction stops. And so the limiting reactant is the starting point for all of your calculations because it controls everything. So if this were a case, our example was not one of these cases, but in the video tutorial, I do a case where there's a second product. We would just use the limiting reactant to calculate any other products that are in the example in the problem. And then we use the limiting reactant again. So again, it seems like a lot of steps, but they start the same way. In some case, in a very real sense, it's like copy pasting most of your work each time. So you're going to use the limiting reactant again, just like we used fluorine, 10 grams of fluorine as the start of our problem. That's going to tell us how much is used. And then the leftover is going to be initial minus used. And that's how we do a limiting reactant question. I'm going to pause for a moment just in case. Okay. So that's really all that, that's really all there is when it comes to sort of how much mass am I going to make, how many grams am I going to make, and so forth. And now we've added in how much leftovers will we have. And we now know how to deal with that with the whole concept of limiting reactant. As far as stoichiometry problems can go, there's one other type. Well, yeah, kind of one other type. That's a little bit different than the others. It's when we want to calculate how much heat is going to change. And so for that, every chemical reaction has an associated heat change that we call the reaction enthalpy, which is given the symbol delta H reaction. This is the amount of thermal energy, aka heat, that is released or absorbed by a chemical reaction at constant pressure. So meaning doing it, say, in open air counts as constant pressure because the air pressure doesn't change in very meaningful ways throughout the day. So as long as we're doing it in an open air, this part of the definition is kind of like not necessary. So how does it look? Oftentimes it's written beside a balanced chemical equation. So not in the balanced chemical equation, but beside it. So for example, this chemical reaction has a delta H reaction of minus 2602 kilojoules per mole. Just a reminder, since it's been a while since we talked about energy in the sense of heat changes, that remember exothermic meant that we have negative heat values. So our interpretation of this number is that this reaction will release this much heat. And so we can think of, as far as incorporating energy into the recipe, we can think of heat being released as heat being a product here. So if we really desired to, we could put plus heat at the end just to show we're releasing the heat. It is not necessary to do that. However, in Chem 1b, it's a nice trick to be able to say, oh, it's exothermic, so the heat should go released. It's a product. Anyway, that's for Chem 1b. And then for endothermic, it's the opposite, positive values, and it means absorbing heat. And so if we wanted to write it in the chemical equation, we could put heat as a reactant. It needs to be consumed or taken in to make the reaction proceed. So we're just revisiting the topics of endothermic, exothermic. There are definitely a lot of different examples in nature of endothermic and exothermic reactions. And so it might be important to be able to calculate how much heat is going to be released when we do something. And so examples of that, I want to say every ionic compound synthesis, I can't confirm it, and I'll try to go slowly. I can't confirm it because I haven't looked at every single one, but I'm pretty sure every single ionic compound that can be synthesized in nature has an exothermic chemical reaction. And so this is actually sodium chloride being made from sodium metal and chlorine gas. The gas is literally poured into it, and all of a sudden you see a bright flash, meaning a lot of energy is being released. And in fact, if you touch the flask, that would be a bad idea. The walls of the flask are extremely hot. Once it cools down and once the glow sort of dissipates, what you'll find is that instead of seeing a shiny metal and sort of an atmosphere of green chlorine gas, instead what you'll find is that the walls of the glass are sort of caked in salt, basically. So it's a pretty interesting visual to sort of see it happen. And you can find those visuals on YouTube. You can look up making sodium chloride or something along those lines to see it. It's pretty cool. But other reactions that we have, combustion is the common form. And so I talk about combustion and how to identify them in one of the pre-lecture videos titled Combustion Reactions. Remember that there's a very common theme. It means you take some kind of organic fuel, AKA, something like wood, you add oxygen in it, and which is abundant in our air. And the products of combustion are always the same. It's CO2 gas and water. So this is another example. This would be considered what kind of thermic? Endo, exo. So I can feel the heat coming off of this reaction. It's being released, so it's exothermic. And then this might be one that we don't sort of realize, but you can actually do it yourself to prove it. This is baking soda vinegar, and this is the reaction for baking soda and vinegar. And in our very last lecture, we're going to talk about how to predict this reaction. But this is the formula for the acid in vinegar, acetic acid. So we should actually know how to name this. Sodium, and then it's CO3 with an H in the front. So that's sodium bicarbonate. Also acceptable, sodium hydrogen carbonate. That is also acceptable. When these two get together, they make CO2, H2O, and sodium acetate. The CO2 is what gives the bubbles. And what I mentioned about the heat is that this reaction is actually endothermic. So if I pick up the cup with my hand, what is it going to feel if it's endothermic? So that's actually something, if you have these ingredients handy, you could try it yourself. It's going to feel cold because endothermic reactions absorb heat to make the reaction go. They'll suck the heat right out of your hand. And so it'll feel cold to us when one of these reactions happens. All of these reactions are examples of why we study chemistry. It's because we remember that the chemical bonds are formed in all of these substances because the atoms are trying to change the energy of their electrons, giving them away, adding them, putting them in new orbitals. But every time we make a Lewis structure, we make a new structure, new connections, we're sort of making a transaction. We're taking away energy from the reactant bonds, and then we're adding that energy back into product bonds. So if we think of it in terms of Lewis structures, it's basically the reason why we have endothermic and exothermic reactions is because energy changes when the reactant bonds break and reshuffle into product bonds. And that's something that we can actually calculate and something that you will calculate using the energy of bonds in Chem 1A. But our task right now is to do stoichiometry calculations with enthalpy. And so we have this example. The reaction enthalpy is a number specific to the exact mole amounts in a balanced chemical equation. So the math that's involved has to do with making relationships among our different species in the chemical reactions. In this case, if we're interested in the heat changes, we want to know the relationship between maybe burning a certain amount of fuel and calculating the amount of heat. So that means that there's a slight addition to how we can make conversion factors with reactions. We can always use the coefficients to connect two chemicals, but we can also use the coefficients to connect to the amount of heat being used. And so that means we can use the enthalpy value as a conversion factor for heat changes. And to demonstrate that, we can do what is the conversion factor between the molecule C2H2 and the heat. So according to this reaction enthalpy, for every 2 moles of fuel that I burn, this is actually acetylene. If you know your sort of fuels, it's a part of like torches. 2 moles of this molecule will release, because of the negative sign, 2,602 kilojoules of heat energy. That means that there's only one slight addition to our stoichiometry. We just have to add, you can always make a conversion factor between moles of anything to the amount of heat that it releases. The negative sign indicates in the calculation that you're going to be releasing this heat. So remember, the negative sign might not seem like a big deal, but it tells us whether we expect it to be released or absorbed. So these are our conversion factors. And now what about the conversion factor between the amount of heat and the oxygen for combustion? That's going to be minus 2,602 kilojoules per 5 moles of O2. After this, stoichiometry problems become the same thing again. So it's still the same kind of issue with the same strategy. There's only one slight kind of difference we have when we do a question like this. An acetylene torch carries 25 grams of C2H2. This is acetylene. What is the heat change in kilojoules for its complete combustion? So again, what I like to do is start with the central theme and then work my way to what I should be doing. So what is the goal of stoichiometry? The goal is the mole. We want to go from moles given to moles desired using the balanced, I'll just say B, chemical equation. So I'm really abbreviating. Now, what do I desire? Well, this is the only time it's a little bit different. Instead of desiring a chemical, I actually desire the kilojoules. My given number is going to be 25.0 grams of C2H2. So while we can say, oh, now that I've written my numbers and my chemicals, I know that my given is C2H2. So I'm going to cross out the word given and do C2H2 and say, okay, that's my flow chart there. Now, this is where I say it's a little bit different because now we see it's not really moles of desired. It's more like kilojoules. Well, I guess kilojoule doesn't need a conversion to kilojoule, but we can still write the arrow. That's the only time it's a little bit different is when we're dealing with heat, but it goes the same way. Now I need to convert 25 grams of my fuel to moles of my fuel. Use the balanced chemical equation to turn it into, in this case, now it's kilojoules. So how's that going to look? I'm going to start with my given, C2H2. What's my first conversion? I see the arrow is grams to mole. That's the molar mass conversion. So I've actually already done that calculation, but if we were to do it, it would just be 2 times the mass of C plus 2 times the mass of H and put it down here. That's going to be 26.036 with the significance ending on the 3. Grams of C2H2 is a mole of C2H2. So that's just from the periodic table. And now what we just determined, I need to go from moles of my given, C2H2, to desired kilojoules minus 2602. So minus 2602 kilojoules is 2 moles of C2H2. with that, everything cancels, and we're left with kilojoules, which happens to be the exact unit that we want. So it comes out to minus 1250 kilojoules. What does this minus mean? One more time, it means released heat, which should make sense after watching the video of combustion. Combustion means burning things, essentially. It's a more sophisticated way, I guess, to say burning. So it's going to release a lot of heat. Also a giveaway is the fact that we mentioned it's a torch. So torch is fire, probably should release heat. So that's sort of the extra little bit on the stoichiometry problem. The rest of the course, actually, starting with the next slides, is basically how to get to the central theme. The goal is the mole, using different units as my starting units and using different units as my ending units. And really, this doesn't require brand new math. What it requires is pulling from our chapters. So we've actually done all the work of doing the math prior to this, learning the math prior to this. What we're going to do is we're going to extract how to do calculations from the gas chapter and how to do calculations from the solution chapter in order to answer the whole set of possible chemistry questions of how much am I going to make. And so we start with gas stoichiometry. Oh, and then just by the way, by definition, negative heat values mean releasing heat. That is the definition of a negative sign for heat. So it released heat. Positive means it absorbed heat. And it's really just, that's the definition. So for example, we can talk about making CO2 by burning carbon. So if you take carbon and you burn it, you add oxygen to it, you make CO2. How many liters of CO2 can we produce from 500 grams and plenty of oxygen at STP? While this might seem intimidating, oh my gosh, now we're talking about liters and STP and whatnot. Really, what I'd like to emphasize is that the best sort of strategy is to start with the central theme that will always be there and then work your way around. So what is the central theme for a stoichiometry and a how much problem? My goal is moles. I want to go from moles given to moles desired. Okay, how do I do that? This arrow is the chemical equation. Now let's identify what information is given and what I desire. Given, desired. Well, I desire how many liters of CO2. So that's what I'm going to put first. And I mentioned this previously, I'll mention it again. Sometimes it's easier to start by identifying what you want before identifying your givens. So I desire liters of CO2. So by process of elimination, the carbon, which makes sense, has the number with it, is the given. So it's going to be 500 grams of C. Now that I've identified my units, I can make my strategy more tailored to what we're doing. I've identified the given is the amount of carbon. So I'm just going to replace the word given with carbon. The desired is the CO2 amount. So I'm going to replace the word with CO2. Now I have my flow chart. Take the givens, turn it into moles, take the moles of desired, turn it into liters. Now, we've done this several times. How am I going to do this first step, turning grams of carbon to moles of carbon? That's a molar mass conversion. The middle arrow is my balanced chemical equation conversion. I'm going to use my information there. But my desired is going from moles of CO2 to liters of CO2. How do I turn moles of a gas into liters of a gas? So this is kind of the final step of assessing what tools do I have to do this. And remember that I mentioned it's pulling from previous chapters. This is our gas chapter. I want to go from N to V at STP. So what is that going to end up being? Use PV equals nRT. So it's a callback to all of that, but that will tell me how to turn moles of a gas back to liters of a gas. And again, it becomes more obvious when we do this flow chart and just assess unit to desired unit. What do I do? And this is moles of a gas to liters of a gas. And that tells me, oh, I need to recall that information. It's PV equals nRT. Now, additionally, because this is STP, there's actually another conversion we have. If we go back to that chapter, again, this chapter was called, actually, it was just called gas law. I think it was lecture 6 or lecture 5. There is one more sort of number that is optional to know, but it saves time. It's the molar volume of gas, right? And that's 1 mole of gas, any gas, is 22.4 liters. And so that can become a conversion factor as well. So that's exactly what we're going to be doing. We're going to set up 500 grams, convert it to moles, using the molar mass. So that's from the periodic table. And then we're going to do, using the coefficients of the balanced equation, 1 mole actually turns into 1 mole of carbon dioxide. That gives me this many moles of, it's not rounded yet. But then I'm going to use PV equals nRT. The answer becomes my N. And then let's not forget what R is. It's been a while, so maybe, well, for us, it hasn't been a while because, you know, it was only like 2 weeks ago. If this were a semester class, it's been a while. 0.08206 atmosphere liter per Kelvin mole. The T is the same T as STP, and the P is also the P in STP. So that's 273.15 Kelvin and 1 atmosphere. We're going to plug that into our calculator to get that we will make, under these conditions, 933 liters. The major idea is that while this looked like a different problem, if we treat it with the same type of going into it strategy, it becomes much easier to sort of focus in on what's the different scenario and how to tackle it. There is only one arrow, there's only one arrow that was different, and that's what I needed to focus my attention on. And so the question became, well, how do I turn moles of gas to liters? That's PV equals nRT. Okay. Giving us our strategy to get to our answer. That's the full method. There is, you know, as I mentioned, depending on the scenario, different ways to simplify. Again, only if we're at STP can we use a molar volume, but we could use the molar volume here. It would save us this equation. there is another way that we can do this calculation. Well, not that specific calculation, but this example calculation. How many liters of gas at 25 degrees Celsius and 1.50 atmosphere are needed to produce 9 liters of HCl? So the equation is H2 plus Cl2 makes HCl. Again, the central theme is moles given to moles desired. Now, what do I desire? My H2. So that means since the how much or how many goes with the H2, that's what we're looking for. H2. So desire. What am I given? I'm given information about HCl. So my plan starts to come to fruition. I have pressures, I have a volume, and I have a temperature of HCl. So I need some way to take my givens, turn it into moles, and then take my moles and turn it back into volume. How do I do this calculation? That's PV equals nRT, right? To go from PV and T to moles, that's N. And then to go N back to V, what am I going to use? Hey, it's the same thing. PV equals nRT. Because it did not say that the temperature or the pressure were changing, we can reuse the same values. So it's just going to be PV equals nRT, do the stoichiometry calculation, and then go back to PV equals nRT. And so if you actually plug in these numbers, again, remember that we have to convert temperature needs K for a gas calculation. If we actually plug in these numbers, we get this quantity of moles, 0.5518. Then we ask, well, this is how much moles given. To go to moles desired, HCl to H2. 2 HCl makes 1 H. So that's where this comes in. 2 moles of HCl for 1 mole of H2. And I get this value. This is how many moles of H2 I will make. And then moles to volume of gas. Okay, again, one variable to the other. I'm going to use PV equals nRT again. And then just to emphasize one more time, I'm reusing the same temperature and pressure from the problem to do this. Because it did not say that I couldn't do that, basically. The temperature did not change during the problem. And then just to remind ourselves, I'm putting this N value in here. And I get 4.5 liters of H2. It seems kind of like a lot of work, right? So is there a shorter way? Especially if we take a moment to look at what we did, it says if you take 9 liters of HCl gas and you react it, you actually get 4.5 liters. Now, I don't know if you've stared at numbers long enough as I have to sort of see that there's an interesting relationship between 9 and 4.5. It's one of those things you don't really pay attention to, but it turns out that 9 and 4.5 are a difference by a factor of 2. And so it's very interesting that with all of these complex calculations, we get such a sort of simple difference between the two. So it kind of suggests that there's some sort of hidden magic that maybe it doesn't seem all that hidden if you take a moment to look, but we're going to talk about it explicitly. There's a hidden magic to this kind of question, and it involves a fact that we, in our calculation, had to change a gas, convert a gas in the beginning and convert it back at the end. if I take a moment to sort of just write the multiplication that occurred, we took our volume and then we did PV equals nRT to it. And so if we look at the equation one more time, it required that we did V times P over RT. So I'm writing it like a conversion factor. And then we did the mole ratio between the two, and we got a new volume, a new moles, right? But then we used PV equals nRT one more time. And when we did that equation, it actually flipped the calculation. Again, to get it in the beginning, it was PV over RT was what I plugged in. To solve for it at the end, I did nRT over P. So they're the flip of each other. What ends up happening is that the gas law part of the calculation actually cancels out. RT with RT and P with P. What it ends up is that what we find is that the volume and then the balanced chemical equation actually simplify to the new volume. What this is really saying is that when we are doing, and we have to be very careful with this, it only happens when we're doing volume of gas to volume of gas conversions. But when we do that, we can simplify our math quite a bit. It's really just take the volume and then use the coefficients as a cancellation, as a volume to volume conversion factor. So to look at this problem one more time, the simpler way to do it would be to directly go from liters given to liters desired using my given information, and then only, and we have to be very careful, only works for volume given of gas to volume desired of, volume desired of gas. There we go. But when we do that, they become purely liter, volume to volume conversions. And so we can say 2 moles of HCl makes 1 mole of hydrogen, but since they are both gases, it also is true that 2 liters of HCl makes a liter of H2 gas. Or 2 milliliters of HCl make a milliliter of H2 gas. Or 2 cubic centimeters of HCl make a cubic. What I'm getting at is the unit doesn't matter since it's just a ratio, that we can use whichever unit we want. But this actually gets us our answer in one sort of simple math step. I should stress, this is a nice trick. This is a nice sort of shortcut. Remember that if I wanted to, I could have done it the full way that we've been doing it. Moles given to moles desired, connecting the arrows, and doing all the steps. This got me the same answer and works just as well. But what I'm saying is that for very special circumstances, we can really shorten our work. And that's under the conditions where I have a volume of given gas and I desire the same volume of desired gas. Then these become really nice volume to volume conversion factors. If you're wondering why this is the case, why it's true, it goes back to the kinetic molecular theory. Way back. The kinetic molecular theory told us that for every gas, it sort of acts like a bunch of tiny little dots that are just bouncing around the walls. It doesn't matter what kind of gas it is. One gas versus another gas will still look like tiny little dots bouncing around. And so a mole of HCl will take up the same amount of space as a mole of H2 because they look and they supposedly act the same. And so because of this, the only thing that differentiates one gas from the other is the amount that's present. So if I have 2 moles of HCl, it will be twice the volume as 1 mole of H2. That only works because they're gases and the ideal gas law. When that happens, we can use this conversion. Woohoo! This summarizes this lecture. Basically, the idea is the goal is the mole, and I want us to think of that as our central theme for trying to get to a desired. We want to make sure we understand that this is always going to be the center of point of what we do. The rest is just going to be how do I convert to moles or how do I convert out of moles? Now, the asterisk is indicating we could also replace heat to moles in the case of enthalpy, but it works the same way. And so we've utilized this strategy for a limiting reactant problem, for enthalpy problems, and now for gas stoichiometry problems. Again, the main idea was always the same. The difference was figuring out how do I go from my starting point to the center? How do I go from the center to my end point? And that was it. Now, here's a bonus practice. Actually, I was mentioning the module. So I have this so that it's printed into your notes if you're downloading the notes, hopefully. This is another stoichiometry problem. I have the answer on module 9 along with the video of how to do it. So I'm going to leave this for you to take a look and think about. And if you'd like to check your answer, it's in module 9, along with a video of myself going through it. Okay. But I'm not going to do it right now. I leave that for the video. But I think it's time for our break. I think we should have a break. What I'm going to be doing is starting the next lecture, which is actually a good thing. I'm glad you're here for that, because the next lecture reintroduces solutions and some very important calculations we do with solutions that we saw previously in the solution chapter. So that's what's coming up in the next lecture. But let's go ahead, stop the recording and take our break.